Welcome to this lecture of the course Computational Hydraulics. This is module number 4, surface water hydraulics, and in this lecture class I will be covering unit 7, that is unsteady 1D channel flow. Learning objective: at the end of this unit, students will be able to solve unsteady channel network problem using implicit approach. Problem definition to solution: this is our total course structure. In this case, we are considering that discharge y is a function of x and t. At the same time, y or flow depth, that is also a function of x and t. In our previous lecture class the lecture with steady channel network flow with or without reverse flow situation, we have discussed the same problem. In that one, we have conceptualized our problem as q as a function of x and y as a function of x. So, this is essentially a steady problem and this is unsteady problem. In steady problem, the quantities q and y, these are not varying with t, but in unsteady problem q and y, these two quantities are varying with time. So, this is the first assumption, that our discharge and flow depth, these two values are varying with time. So, what is our hydraulic system? Hydraulic system is natural maybe channel network. Let us say this is my channel network, and let us consider a problem where I have some specified condition at this point and this point and end point. This is our junction as per definition. Now, as per conceptualization in steady state flow situation or steady state channel network situation, we have considered different q values for different channel reaches. This is let us say channel reach 1, this is channel reach 2, this is channel reach 3, and for these two channel these three channel reaches, our discharge and flow depth, these two quantities will vary in case of unsteady case, but also with time, but in steady state case we will have fixed values for discharge and y. Now, our steady state problem, that was boundary value problem, because we need boundary value only to solve that problem, but unsteady problem we need to specify the initial condition. So, during mathematical conceptualization, so hydraulic system is channel network, maybe this is channel network flow. Governing equation, we need governing equation for this one. We have two quantities, that is q and y. So, we need two governing equations for this problem. At the same time, we also need initial condition, because what is the initial state that is important for any unsteady problem. At the same time, we also require boundary condition. Boundary condition may be fixed or time varying boundary conditions. Either it can be in the form of time varying discharge or time varying depth, or fixed depth or time varying discharge condition. Now, we can discretize our domain, which is essentially 1D domain, each channel network channel reach. In this case, we can consider uniform grid. Also, we can solve the same problem for non-uniform grid system, and in this case I will be talking about a special kind of finite difference technique. And finally, the equations for this problem is nonlinear in nature. So, we need to apply this nonlinear solver, either that is iterative approach or Newton-Raphson approach I will be utilizing for solution of this problem. So, let us see what is the problem we want to solve. Now, let us consider this network. So, we have channel 1, channel 2 and channel 3. All of these channels are of 5000 meters length, and we have two specified discharge condition at upstream. So, let us say these red dots, red dot 1, red dot 2, these two are specified discharge condition in the upstream, and we have specified depth condition in the downstream section. An internal blue node, this is our internal junction condition. We have elevation of 0, this is +1. For this node we have +2, for this node we have +2 for elevation. Now, for this problem we can see that this discharge is in meter cube per second, and it is varying from 50 and it is reaching a maximum value at 2000 seconds, and again it is decreasing from 150 to 50, and after this 4000 seconds we have a constant 50 meter cube per second discharge for both the inflow sections or inflow junctions. So, we have two inflow junctions 1 and 2, and for both of these junctions we have specified discharge condition, and this discharge condition is time varying. And downstream section, and that is at this point we have specified flow depth, and interestingly in this case we have constant flow depth over time. So, 1.43 meters, this is constant flow depth at this point. So, it is not varying with time. Now, we need to solve this problem. So, for solution as I have already told, we need the specification of initial condition. So, for this problem which is with these 3 channels, let us say we have a positive flow direction, this is our positive flow direction, this is our positive flow direction, this is 50 meter cube per second, this is 50 meter cube per second. On the downstream we have 100 meter cube per second, and we have uniform flow condition in this channel network with flow depth of 1.43 meters for all the channel reaches. So, we have a specified initial condition, that is 50 meter cube discharge for these 2 upstream channels, and for this downstream channel of this junction we have 100 meter cube per second, and this is our initial flow directions. So, at this junction you can see that 50 meter cube on this side it is going 100 meter cube. So, unlike our steady state problem, in this case we need to specify the initial condition by satisfying the continuity condition, because initial condition means it should satisfy the physical problem. So, in case of our steady state problem, we have seen that from any arbitrary initial condition we can get the final result, which is a steady state flow condition. So, initial condition in case of steady state problem is nothing but initial guess for the problem, steady state problem. But in case of or unsteady state problem, initial condition is important, because that should satisfy the physical constraints or physical equations. So, discharge continuity is one equation that should be satisfied, and we have a flow depth for all these channels as 1.43 meters. That means at this point which is the blue point in the center, it is the internal junction point. For internal junction point our energy condition is also satisfied, because from all sides this channel ends or the starting section of the channel 3, these are at the same elevation. So, we have energy continuity and discharge continuity, these two are satisfied at the beginning itself. Now, I can list other things. So, first assumption is our channel flow direction, because we need to number our channel sections depending on the flow direction. So, I will try to follow the same convention that I have used for our steady state flow situations. So, in this case we will consider that we have 1, 2 and 3, these are junctions or boundary junctions, and number 4, which is as internal junction point. So, we have 3 channel reaches 1, 2 and 3 and 4 junction nodes, out of that 3 are boundary junctions. So, let us see what are the background information for this one. So, channel data, we have channel number 1, this is 5000 meters length. So, this is channel number 1, we have this is inflow, this is also inflow. So, we have this as channel number 1, junction node 2, 3 and this is 4, channel 1, 2, 3. So, now for this one, for channel 1 length is 5000 meters, width is 50 meters. So, in this case we are considering rectangular channel section. So, we have 0 slope m1 and m2 equals to 0 and this is b or width of the channel, but we do not know what is the depth, that is the function of x and t. Now, channel reach, that means del x 1 for channel reach 1 is 500, del x 2, del x 3 all are 500 in this case. N value, these are Manning's N values, and slope for all channels we have considered the slope. Now, we need to specify the junction continuity or junction connectivity. For channel 1, it is connected to 1 and 4, as we have considered the flow direction from 1 to 4, that is why we are writing the starting node is 1 and ending node is 4. Channel 2, starting node is 2, ending node or a node with the end section, that is 4. Again for channel 3 we have 4, 3. So, these are the information that are required for our problem. Now, next thing is a specification of boundary conditions. This is junction data. In our steady state case, we have utilized same kind of matrix structure, but the problem is in this case we have time varying boundary condition. So, we cannot directly specify the values in single matrix. So, for depth or flow depth, we will write this is equivalent to 1 and discharge is equivalent to 2. Now, with this, if I see this column 2, 3, column 2 is for depth, column 2 and column 3 is for discharge. Now, for a particular junction, this is junction number 1. Junction number 1 is inflow junction or a specified discharge condition. So, if there is specified discharge condition, we will write it as 2. Otherwise, we can directly write minus 5 9, and for junction number 2 also, that is again boundary junction, we do not have any specified depth. So, minus 5 9s, and in this case again we will write it as discharge equals to 2. Now, junction number 3, again we have specified depth value, that is why here we will write it as 1, and we do not have specified discharge condition for our problem. that is why we have minus 5 nines in case of discharge, and for junction node which is internal junction node number 4, we have 5 nines because we do not have flow depth or discharge specified for this junction. Now, for our problem we have 4 junctions. Out of this, so let us say that N1 plus 1 is the number of section in channel reach 1, channel reach 2 and channel reach 3, we have N2 plus 1, this is N3 plus 1. So, in this case, for a particular time step, we have N1 plus N2 plus N3 plus 3 into 2 unknowns. That means, we have depth and discharge. If you add depth and discharge values, we have these many discharge and these many depth values are unknown. So, all total we need these many equations to solve this problem. So, we have 2 N1 plus 2 N2 plus 2 N3 number of equations coming directly from N1 number of segments from channel 1, N2 number of segments in channel 2 and N3 number of segments in channel 3. So, still we need 6 conditions. Out of that, for this internal junction we will get junction continuity. What is that junction continuity for this problem? For this problem we have this junction, and at this junction this is our channel reach 1, this is channel reach 2 and this is channel reach 3. So, we will have Q1 N1 plus 1 plus Q2 N2 plus 1 minus Q3 and 1, this should be 0. So, inflow is coming from our channel reach 1, 2 and this flow is coming out from this section 3 1 of the channel reach 3. So, we have this discharge condition. Next is energy condition, because we have considered that junction or end sections are at same elevation at the junction. So, we can consider that y n1 1 n1 plus 1 equals to y 3 1, and third condition y 2 n2 plus 1 equals to y 3 1. So, we have 3 conditions out of the 6. Now, still we need 3 conditions to solve this problem. So, from our boundary conditions we have specified discharge at node 1, node 2 and specified flow depth at node 3. So, from these we are getting extra 3 conditions. So, now we can solve this problem. So, 2n, 2n1, 2n2, 2n3, these number of equations will be coming from individual segments of different channel reaches, and 3 equations for junction node 4 and 3 boundary conditions, 2 discharge and 1 flow depth condition for this problem. Now, what is required out of this problem? We need to plot the discharge and depth hydrographs at x is equal to 4000 from internal junction node in channel 3 of the network. That means, if we have, this is junction node number 4, 4 to this is 3 at x is equal to 4000. That means, this length is 4000. At this length of channel 3, we need to find out what is the variation of discharge, x is equal to 4000, discharge with time, and this is x is equal to 4000, again flow depth with time. Now, we need to plot these two values. To start with, for this one we need to define the problem. So, problem is essentially, this is governing equation for 1D channel flow, that is Saint-Venant equations are required, one for continuity and one for momentum. This is initial boundary value problem, and this is our initial condition. If you have one this at any particular junction, if we have some extraction or injection into the system, we can use this Q. Momentum, this is the momentum equation, and what is this H? H is nothing but this is y plus z. That means, y is flow depth, z is our elevation of the channel bottom, then H is y plus z. So, for any channel, let us say this is a channel and we have this datum. For this datum, this is at any section, this is our z and this is our y. So, the total thing is H or y plus z. In this case, SF is our energy slope or friction slope. So, in this case we have y as flow depth, SF is friction depth, friction slope, A is cross sectional area, Q is lateral inflow to the system, Z is elevation of the channel bottom with respect to datum, H is water surface elevation, alpha is momentum correction factor, Q is discharge, G is acceleration due to gravity, and we are considering the flow in x direction only, x direction or one dimensional in space. So, this is the flow situation for our problem. In this case, let us say we have 2 channel section I and I plus 1. Then for segment I, for nth channel reach, we can write our discretized form of the governing equation. Now, for this discretization, I will utilize one special scheme. Before that, this is our flow convention that we are utilizing, that is from 1 to n, L1 to NL plus 1, we have positive flow. If L1, if the flow direction or flow value is negative, so obviously the direction of the flow will be opposite in this case, and from junction left to right this flow is occurring. So, for one junction it is negative, for another junction it is positive. For a general variable, in this case, I will just define this discretization. In this case, we have In is one section, another section is I plus 1 n. This is at future time level I n plus 1, I plus n plus 1. So, by considering these 4 points, we can discretize our governing equation. So, for any general variable phi, this Prisman scheme can be written as, for phi we have this psi I plus 1 n plus 1, this value, and I n plus 1. So, weighted addition between these two. So, some value in between will get, again weighted addition or weighted combination of these two will get here, and again this is for a spatial combination, again in time we can again give weighted combination here. So, with theta and psi we can define the problem. So, I plus psi n plus theta. So, in this case again we can use our concept, and what is that? This is again the combination. What is that combination? Combination is psi into our phi I plus 1 n plus 1 plus 1 minus psi into phi I n plus 1, this quantity minus we have psi into phi I plus 1 n and plus 1 minus psi into phi I n. So, we can subtract this and divide it by del t. So, this will give you this del t derivative, and similarly for del phi by del x we will get the weighted combination here. Now, we need to discretize our continuity equation first. So, continuity equation was del q or del A by del t plus del q by del x and minus q equals to 0. So, del A by del t we can discretize like this. This is del A by del t. So, again we can take that weighted combination with respect to psi and get this. Similarly, for del q, this is weighted combination for del a by del t. For del a by del x, we have this theta weighted combination here 1 minus theta, and the last one, this is again our inflow parameter. We can again take a weighted value for this one. So, this is a discretization for the continuity equation. Although this part is linear in nature and the problem is totally dependent on the theta and psi values in this case. Let us say we have psi equals to 1, then we will have one combination here. If theta equals to 1, again that is the changing the spatial derivative. If theta equals to 1, obviously we are considering implicit case. If theta equals to 0, obviously we are considering explicit case because the explicit or implicit consideration depends on the time level of the spatial derivative. So, to utilize this equation in our general Newton-Raphson format, we need to take derivative with respect to 4 variables. So, what are these 4 variables? So, for any segment we have variables y l, for lth segment I n plus 1, then q l I n plus 1, then y l I plus 1 n plus 1, and q l I plus 1 n plus 1. These are 3 variables 1, 2, 3 and 4. Now, we need to take a derivative of the CLI n plus 1 with respect to these 4 variables. So, if we take a derivative of our continuity equation, we will get these 4 terms. Obviously, in this case dA by dy, this is the derivative of area with respect to y, and area is a function of y only, it is not a function of discharge in this case. So, momentum equation discretization. So, momentum equation was d q by a. So, for dq d by dt of a, we can directly write this writing q by a terms. Then we have this del by del x, this is alpha q square, this is 2 and a square. Now, the last one, this is g del h by del x and plus g into SF, this is equals to 0. So, for all cases like temporal derivative, we are taking weighted combination with respect to psi. for spatial derivative we are taking weighted combination with respect to theta, and for others like this one also we are taking weighted combination with respect to theta because it is a spatial derivative, and SF it is a combination of theta and psi, and in this case I have not written the superscript n plus 1 for z because z is not varying with time, z is fixed bed elevation, that means we are considering rigid bed channel here. Now SF can be calculated from Nm square q square r to the power 4 by 3 a square, and if we consider the sign of discharge, then we can modify this one, and modification will be there only in the case of SF. This is Nm square q mod r to the power of 4/3 and a square. Now again we need to take derivative of m l I n plus 1 with respect to the 4 variables that we have utilized for our continuity equation also. So first one is y l I n plus 1, next one is y l I n plus 1, this is q l I n plus 1. Now in this case one should note that in this case we are utilizing these mod values only for the derivative terms which are related to SF. So in this case we have q square term, but we have replaced it with q into mod q. In this case also I have utilized this mod q. Another variable, this is y l I plus 1 n plus 1 q l I plus 1 n plus 1. Again we can see that this mod values are utilized or used for this SF calculation or derivative of SF terms, and in this case we have dr by dy, dA by dy, these values are to be calculated from section dependent values. In this case we have rectangular section. So, dA by dy essentially that is width of the base or width of the channel for rectangular case. Now for each section we have 2 NL nonlinear equations with 2 NL plus 1 unknowns, that is discharge and flow depth. For trapezoidal section, this is a general section because if we utilize different values of m1 m2 we can directly get the solution for different cases. This is for trapezoidal section dA by dy, and this is dr by dy. We can directly get that from this expression, and by changing different values like dA by dy at l I n plus 1 means I should calculate this term with y l I n plus 1. So, I can directly use the value here and I can get the derivative term. Similarly, for others we can calculate the values. Now, this is the algebraic form. If we have the equations from segments, we can write it in general form in the format of Newton-Raphson. So, these are increment values, and this is minus residual for momentum, minus residual for continuity, and these are the coefficients. Coefficients are essentially elements of Jacobian matrix. Now, we can solve this problem with a guess value, and for the problem guess value for next time level should be the value which is specified for the initial time level, and for consecutive time steps we can consider guess value as the previous time level value. Now, after getting this we can directly add it. So, we can start with a q L I n plus 1, this is y L I n plus 1, q this is L I plus 1 n plus 1, this is again this is y L I plus 1 n plus 1. Now, in this case after getting this increment values we can directly add it with a previous time or previous level iteration values like this plus del y L I. Similarly, for other variables this thing is repeated, or this expression is repeated. Now, for this one we have only 2 NL number of equations. Now, I have already discussed that we have 3 internal conditions and 3 boundary conditions. So, we need to incorporate those values within our calculation or expression. So, configuration wise we have started with this configuration starting with 3 channels. First channel linking this node numbers 1 and 4, second channel 2 4, third channel 4 3. So, if we consider our usual discretization approach, so discretization is in the direction of flow. So, this is 1 1, this is 1 NL plus 1, this is 2 1 2 N 2 plus 1, first one is N 1 N 1 plus 1, this is starting is 3 1, this is 3 N 3 plus 1. So, obviously we have these nodes 1 2 3, these nodes are internal nodes. We should utilize these 3 nodes for specifying the boundary condition junction condition at 4, and these 3 nodes should be utilized for specifying the boundary conditions at boundary junction nodes. As per our previous program structure from the steady state flow condition, we have CHL inf, which is channel information matrix. This is 1 2 3. This is the same our same matrix or same table that we have directly utilized. Next is junction information. Only change is there in this junction information. If I compare this junction information matrix with our steady state case, we are not directly specifying the values in junction information. We are specifying the type of junction information available at this node with this junction information matrix. And the third column obviously that is our elevation or junction elevation information, and this is junction continuity. Junction continuity in this case it is simple as per our usual convention. We have 1, 2, 3 and this is 4 junction wise, and this is channel number 1, 2, 3. So, for channel number 1 or node number 1, this is junction continuity. So, node number 1 we have only 1, it is starting from +1. For node number 2 we have only connected channel is 2 and it is starting from +2. Channel number 3 which is connected to this node number 3 and the end section is connected, that is why -3 is there, and internal junction we have 3 channels connected with this particular junction. So, this is +3, -1, -2 because end section of 1. So, this is -1, end section of -2, 2 that is -2, and starting section or first section of channel 3 connected with this one. So, this is +1 +3. So, this is our channel junction continuity or junction connectivity information.